Well, I have to admit that I didn't get a word of that except the one thing in English, but it sounded
Okay.
like a lovely introduction. So thank you for that, and thank you, BCGE, for the invitation. Thank you for the other speakers for these great talks we heard this morning. I'm delighted to be here. So my name is Kåre Stockholm Poulsgaard. I'm a partner in GXN, and GXN is the independent research and consultancy company that was spun out of 3XN Architects 15 years ago. And so I'm here to talk to you about the architecture side of architecture, engineering, and construction. So I will talk to you about robots. There will be some robots in here, but I'll also talk about digitization and computational design. And I think most importantly, how we try to integrate a certain amount of research into our practice across 3XN and GXN. So this is our offices. We are a Danish architecture and research company. We're based and headquartered in Copenhagen. We have offices in Stockholm, Sydney, New York, and now in London. That's our latest office, just opened up. And we work quite broadly, in case you're not familiar with our work. We do work across a lot of different scales, so everything from the master plan level down through to large complex buildings, hospitals, cultural institutions, office buildings, and all the way down to furniture and sometimes individual products. One of our latest things we've designed is a little bird with sensors that you can put in your child's bedroom, and it chirps whenever the CO2 levels are too high and alerts you to open a window, for example. So really try and cover quite broadly working with the built environment, but always with an idea of thinking about how to improve the lives of people in our buildings and how to reduce the footprint that our buildings have on the planet. So this is our office in Copenhagen. If you ever find yourself in Copenhagen, do come by. We're always happy to receive visitors. This is our office from the outside. We're in a creative neighborhood. The architecture school is just around the corner, so we collaborate a lot with these people there. You can just see the top of the new opera sticking up over there behind us. But I think the key interesting thing with this slide is the text underneath the image there. This is what sets us apart. So we are an architecture company interested in and working towards winning competitions and getting buildings built. And we are a research company working towards thinking about how we can improve those buildings. And that sort of relationship between research and practice is something that we've been developing over the last 15 years, but really thinking a lot about over the last 2 or 3 years. How can we make sure that we integrate research more firmly into practice? It's not that research doesn't happen in architectural practice. As you will see, it's a little bit of a different type of research than what Russell and Tobias and Agnes was presenting. We are very much more in the applied thing. Research does happen on architecture products, but if you think about an architecture product, it's really about getting from A to B with as few hiccups along the way as possible. So from render to finished reality, on time and on budget. Thank you very much. So this is all about risk management. You do get to test out new ideas. This building on here was delivered indeed before time and under budget because we were experimenting with computational parametric design to optimize the structure. But you don't get to test out new technologies. You don't know how they're going to work. You don't get to test out a new material on your facade because if it goes wrong, you might be asking somebody to go out of business. And so to deal with these types of questions, open-ended questions, new technologies, new materials, we've got GXN. So in GXN, we rarely do buildings. We usually start from a problem, a theme we can see across the industry, an interest or a research company reaching out to us to help us test something. And the end products of our work can be quite different. So these are just some examples. We have made new building materials from upcycled agricultural waste and seaweed. As you might know, there's a lot of coasts around Denmark. There's a lot of seaweed. It's a potentially interesting material. We have worked some with robotic fabrication, developing workflows for robotic fabrication, thinking about the design aspects of this. We publish a lot of books. All we do when we're doing research is open source, so we try and get it out and influence the industry. We've been developing a lot of computational workflows in collaboration with 3XN and their partners. So this is us. We are the geeks to the architects. We get to be very excited and run a little bit faster sometimes than the architects can and test out new technologies and new ideas and see what happens and break stuff and learn from our mistakes. Or conversely, we get to go into full basement mode and really dig into a problem and follow it over and over again on series of projects, thereby building up knowledge and improving the way we work. So in GXN, we say we've got 3 focus areas. As I said, we are interested in improving the life of people in our buildings and figuring out how we can do that. We're working a lot at the moment with figuring out how to get information from our buildings back to the designers. I should say maybe at this stage that I'm not an architect or an engineer or roboticist. I'm an anthropologist. And when I first got in touch with 3XN and GXN and started working there, I was absolutely mind blown to learn that architects don't get to see their buildings with people in them. I now know why that is. It's not part of the business model. We don't necessarily have access to the buildings, but there's so much knowledge out there that we are trying now to figure out how we get back. So closing that feedback loop is one thing. The other thing I mentioned we're interested in is thinking about how we can improve or reduce the footprint of our buildings on the planet. And the lens we do that through is the circular economy. Tobias mentioned it as well in his talk. How can we create a more circular built environment, one where we can keep resources and materials circulating at as high value as possible for as long as possible, and what does that require at scale? And then we got the digital design cluster, and this is more of an enabler for us for these other value propositions that we put forward than an end in itself. It's fun to play around with 3D printers and robots, but when it comes down to it, what we're interested in is understanding how digital technologies, new types of fabrication, computational design can support these other missions. So why is this important? Well, as I said, I'm an anthropologist. I got in touch with 3XN and GXN to do my fieldwork on them, trying to figure out what makes a contemporary architecture company work, or maybe not work. I didn't know them that well by then. So I'm an organization anthropologist, and one of the interesting things is that the organization you're part of shapes the way you look at the problem of the world. And different types of organizations are looking at the same problem in different ways. So if we're looking at the problem of architecture, as an example, 3XN, when they're getting to the point where they won the competition, very much looking at it as an exercise in risk management, getting to the finished building on time and on budget, where we as GXN, because we work at smaller scale and work with collaborative research projects and external funding, can look at it as a risk-taking exercise. Russell talked a little bit about this at the dinner yesterday. His research institute is very much also into taking big risks because that's where the big payoffs are. These are very different ways of looking at the same type of problems we're facing, problems about resources, environmental footprints, social equity in buildings, the triple bottom line that Russell also mentioned this morning. So one of the things we're trying to do in GXN is think about what are the future trends and technologies and concerns that we should be thinking about, and how can that influence the architecture that happens in 3XN. And so I always really like this quote here from William Gibson. If you're not familiar with William Gibson, he is a science fiction writer who wrote Neuromancer, and in that book from the 80s coined the word cyberspace. The quote here, "The future is already here, it's just not very evenly distributed," of course has an economic aspect. Certain people have more access to the future than others, but there's also a very sort of simple aspect of this is certain people will be working closer to what the rest of us are going to be working on a few years down the line. Somebody is already right now working on inventing the future. I think we saw some great examples of that from all the 3 speakers here this morning. And so if we as architects want to know about the future, we need to go and work with these people. And so it used to be that if you wanted to know about the future of corporations and technology in the 80s, you would, as William Gibson, go to Tokyo and be inspired by that. Genève 2022 might not be the worst place to learn about the future of robotics. For some time now, at least, Copenhagen has been the place to go to if you want to know about the future of food. And it has been so because of this place here, Noma. Some of you guys might know Noma. Noma is a Danish restaurant. It's based in Copenhagen. It's a portmanteau, Noma, of the 2 Danish words for Nordic and food, nordisk mad. And Noma has been pioneering this approach to cooking with Nordic ingredients they actively go out and find in the forest themselves and find in the bushes around the cities, turning that into high-level cuisine. And Noma has been awarded the best restaurant in the world several times, at least 4 times, I think maybe 5 now. I've stopped counting. But the 2 first times, or the 3 first times, was in 2010, 2011, and 2012. And when they got in touch with us in 2012, the pressure was on. So being nominated the best restaurant in the world 3 times in a row means you got to innovate. You got to figure out what you're doing next. And they came to us with the idea of building a food lab. a place where they could bring in all the chefs, all the different partners they have. So Noma has a lot of chefs coming in from all over the world to work with them. A place where they could experiment with new dishes, and a place where they could showcase all these wonderful Nordic ingredients that they go out into the forest to collect. So there's only two problems at this stage. It was a dream job for any architect, of course, but that was that the food lab had to be in a listed building where it was impossible to do a lot with the interior because pretty much everything was listed. We couldn't do anything with it. And Noma didn't have a lot of money. It turns out that if your restaurant is reliant on going out and picking your own food that you cook, you don't really make a lot of money. Who would have thought about that? But to solve this issue, the architects and GXN worked together to create this sort of fairly simple shelving system consisting of these units that could be placed around the existing building elements and thereby sort of carve up the space and create these exhibition areas, create the kitchen area, even put in a little herb garden, and set the infrastructure in place for the food lab. Now, the reason we're talking about this is the other part of it here tonight, is the other part, and that's the issue about the money. In order to do this on a very limited budget, the architects were working with a full design to fabrication workflow, which from the researchers here, I'm sure they have been delving into this a lot before us, but in 2012, this was the first time for us in a commercial project doing this, and we were doing this at a fairly small scale. But basically, the architects, when doing the designs of these cassettes and these systems, were working closely with the fabricators and making sure that any design was incorporating all the fabrication constraints so that we could send the files to them and they could quickly produce the individual shelving units. That also gave some design freedom, so we could have a little bit more freedom in how the shelving units were working and so on. So that way of thinking has then found its way into a couple of other 3XN projects, and this is probably one of the larger ones. So this is the Sydney Fish Market. It's a fish market in Sydney, but it's a regeneration project taking over the site of an old fish market, turning that into this new big building here, which is both a fish market but also a piece of public infrastructure. It's a place where there's going to be shops, restaurants, public life, and so on. It's huge. That canopy there that sits over the top is 200 meters long, and that's really what from an architectural point of view creates this project. The canopy is the identity, of course, but it's also what allows for quite a flexible floor plan underneath. So this is the first project that 3XN and GXN went into a competition with without any other partners and won as one team. The interesting thing here in this competition is that if you draw a roof like this in a competition, you might quickly disqualify yourself because people will ask very sensible questions about what does this cost to construct? Is this even within budget? And so already in the competition phase, the architects were working with GXN and the computational design team there to create a model of this roof and then start looking at how the design expression and the fabrication constraints could work so that all of these cassettes could be standardized. These cassettes are 9 meters, by the way, also. So again, quite huge. So that we could keep costs down on the roof. And while we had the model, we could then also start doing other interesting things. So we could start running a lot of simulations, looking, for example, at solar and place photovoltaics on the roof so that they optimize for best energy production. We were looking at water. When it rains in Sydney, it pours. So having a massive roof like that requires leading the water off it quite efficiently, which is also something we had to put into the competition. But rather than just lead the water off, so we were creating these scripts, very simple scripts, to just follow the particles as they're floating around on the roof. Rather than lead the water off the roof, we decided to lead it in and try and collect the water and build that together with a larger biofiltration system that sits on the side so that we could recycle rainwater and grey water from the fish market, and now believe that we can recycle approximately 70% of all water that's being used in this fish market. So the story here is really about one of the principles in how we try to bridge this gap between research and practice, and that is experiment and then scale. So learn about a new technology, a new approach, computational design, design to fabrication, how to integrate fabrication constraints into your early design. And then once you know what works, you can scale it up in larger scale projects at 3XN. So here's another example of that approach. This is a project called Digital Factory. The idea is to use what is called robotic hot blade cutting to create a double curve formwork for architecture. So you can control the curvature of that little warm blade there with the end effectors of the robots. And you can control it in real time, and they cut out this formwork, which you can then use to cast curved concrete, which would otherwise be quite expensive, and as we heard this morning, wasteful to make using normal formwork. There's a lot of partners involved in this project. The key of them was Odico Formwork Robotics, the robotics partners, but also a lot of mathematicians from the Danish Technical University. And you need the mathematicians on a project like this because, as we were hearing from Russell, there's a lot of translation going on from design to the robot code. In this case, for example, the blade is controlled with a mathematical construct called Euler Elastica. That's what allows you to computer numerically control this in real time. Designers in any of our software don't use that, and so one of the key things we were developing there, besides the robots, was also developing algorithms to interpolate from one geometrical construct to the other. And so we were doing a lot of tests, not just testing the robotic setup, but testing, and this is where GXN came into the picture, testing the design setup and that interpolation, figuring out where was this efficient, how far could we go, where did we get different types of cuts that we could use, and what couldn't we use. So we were doing a lot of different cuts, testing out, some successful, some quite not so successful, and then also working in single blocks, extrapolating up to larger sort of formwork like this, where we had to work across multiple blocks. So from an experimental point of view, what this allowed us to start thinking about was the segmentation of complex geometries in surfaces and how to deal with that computationally. This is what allowed us to develop the design workflow for this. This is what allowed us to create all these beautiful mockups working with Odico and others. This way of thinking, again, learning from working with the robots and the robotics team, has found its way into another large-scale project, this one here. This is the IOC headquarters in Lausanne in Switzerland. So what you have here is Swiss execution in process. It's designed by 3XN. GXN were also involved. One of the key things that GXN were thinking about there were these curved concrete surfaces. I'm going to talk about the computational side of this project in a second, but 3XN, GXN built a fairly complex model to control this project, control the geometry of this project. And when it came to actually building the project, getting the concrete right, the engineers got in touch with us and asked us to qualify the production model that was being created and work with the engineers on site to figure out how to actually measure whether the formwork was conforming to the model, since we had the most complex side of this model. And so working with some of the insights again around how to segment and understand complex geometry across these large surfaces, we were then able to help the surveyors figuring out where to go and survey, where to put your little points, and how to create a point cloud that we could then test. And I'm happy to report that this was Swiss high precision. There was very few tweaks that needed to be made, but that then led into the production of the piece itself. And you can see sort of it develop, and here it is once it's done. So think about computational design and the IOC headquarters. This is an interesting case also for what these tools allows architects to do. As you might get from some of these, basically one thing these new computational workflows, these new computational tools allow us to do is control a project much longer. If we control the model, we actually control the project, and we control the interaction with the different partners that we're working with. And we have more control of the geometry of the project as more and more partners come on board and start talking about price, cost, engineering, facade, and so on. So the IOC headquarters is designed with this notion of capturing the energy and symbolism of an athlete in motion. So it's a very dynamic building. It's a very open building. I think the sort of most physical manifestation of that idea of capturing the symbolism of the games is the central stairs, which is quite literally the Olympic rings falling down through the building. There's actually an intern who came up with this idea, but then the team had to work through and of course develop it. There was a lot of computational design going into this, getting the threads just right, prototyping and so on. But if you go back to the symbolism and start thinking about the facade of this building, this is, at least for us, a fairly complex facade. It's a double skin facade, so you have to deal with the curvature not just of the outer skin, but also the inner skin. And basically, all of these elements you see up there are non-standard, both in terms of the elements themselves, but also in relation to each other. And so moving from design intent to actually finishing the building required a lot of control of that as we start to detail it. So I'm talking a little bit about the design drivers of this building also to discuss another principle. We could call this design before software, design before technology. For us, it's never the technology that drives the design. There will be a design intent coming from the competition and from the client and from these interactions, and then it's up to the team to figure out how to solve that. And this is an example of that. So the key question with this project was, of course, how to go from render, from early composition sketches, through construction, and to the finished building in a way where the whole thing is actually looking as it was first intended and planned. So one of the key things for us when working with these parametric and computational workflows is a very simple fact that once you design something in Rhino or Revit in a piece of software, geometry translates to data, and data can translate to geometry. And this is one of the first projects where we took that statement quite seriously. And as we started up on the project and got going, the team built a data model for the whole of the project, so that each individual element, we had an identity of it and could control individually and understand where they were. And so based on that model, we could then start passing data, for example, back and forth between different software environments. So we could work, for those of you who are designers in Rhino, when we were working at the larger detail of the building. And we could work in Revit when we had to go in and detail the individual elements. And we could continuously shift packages of data back and forth between these to see how, for example, a detail somewhere in the facade would propagate through the whole thing as we had this linked model. And so this gave us a lot more control as we were starting experimenting with this building and getting more engineers involved. So as I said, there's a basic sort of parametric principle here of being able to do variation studies of the facade, test out what that means for different things. We can start adding in the simulation aspects, so solar shading, for example, and figure out how to, while also thinking about the design, optimize the facade for that. This, when it was opened in 2019, was awarded LEED Platinum, LEED version 4, with 93 points. So it's a fairly sustainable building as well. And we could start also integrating then concerns from the engineers, thinking about the angle domains, for example, how much these angles for the trusses of the facade could be. And all of this allowed us to then, over a series of months, work with all the different specialists and pieces of expertise and integrate that into a model and continuously evaluate with them how the facade was performing from all these different perspectives, and then align while still keeping control of the design intent. So just one story why that became quite important. Even after a lot of this was solved, we were hit by a little bit of a curveball. So as you can see with the double skin facade, you have a little bit of space in there between the inner and the exterior. That space varies in size because of the curvature of the facade itself. After a lot of this was solved, we were hit by a standard regulation Swiss cleaner, which we had to find a way to make sure could be all the way across this building. And that actually ended up messing up a lot of the sort of early interaction stuff. And so the team had to go back to the model, figuring out, what are the dimensions, develop some very simple scripts just to try and test what that would mean. This is just kind of getting the start of it, and then we could start propagating that into the different aspects of it. And then start exporting packages again to the engineers, get their input and feedback, integrate that back into the model, and constantly then seek to minimize the space between the two facades while also making sure that there was enough space for the standard regulation Swiss cleaner. And then get to the final facade here. What do you have here? So I want to end on a little bit of a maybe lighter note. We heard some very interesting and forward-thinking and innovative presentations this morning about technology, about robots, about 3D printing. This last project here is a little bit of a different kettle of fish. But I'm often reminded of this quote attributed to Cedric Price: "If technology is the answer, what is the question?" And we got to think a little bit about this on this project here, which we were doing with the Danish AM Hub. So the Danish AM Hub is an organization that's set into the world to introduce 3D printing to Danish industry. They work with a lot of specialist industry partners. They don't really have a very good, or they didn't at this time have a very good foothold in architecture. And when they got in touch with us, they were asking us not to come up with a new 3D printer or think too carefully about the exact use case in architecture, but rather to come up with something interesting and engaging and maybe a little bit lighthearted, thinking about what the future of 3D printing and robotics might be. And so we were asked to consider a lot of technologies, so additive manufacturing, robotics, machine learning, so potentially the potential for autonomous robots, material science, and so on. And the idea was to be inspired a little bit by Peter Cook and Archigram. This is a Walking City projects, to try and create these, let's say, provocative or sometimes a bit silly futures to kind of just see what happens if we throw that out and see if we could engage some architects. So we did have an architect who had some skills in building robotics working. So that was the first side of the project. We called it the Family of 10. The initial idea was to build 10 small robots and have them hack them with some 3D printing parts and have them walk around and do a bit of 3D printing, which we did. Maybe not all 10 of them, but we got some of them. It's a far cry, of course, from what's happening at ETH and other places, but a fun project nonetheless. Then the second part of that was to build on that mechanical prototyping and try and come up with these sort of, let's say, virtual prototypes. So what could we sort of start imagining on top of this, and then come up with use cases and creating these stories. So one could be that you could have these autonomous robots running around on remote roads, repairing them like this. Or one of my favorites here is the idea, we talked about this just before going in here, both Russell and Agnes told me how silly the idea of printing underwater coral reefs was. This is one of the ideas, I can say, but the idea of having a roaming 3D printer that can print these seawalls outside of coast using sand, and I believe we're looking at a bio-based binder made from oyster glue. So it's all fun and games until the American Army gets involved. So 2 weeks after publicizing this and getting these renders out there, I got a very nice email from a major in an accelerator connected to the DARPA, who was asking me when I thought we could have these swimming 3D printers ready. So I had to tell him we probably shouldn't be holding his breath. And I don't know what they're going to be using them for, but maybe there's a research idea for our esteemed colleagues at the university. So with that, I want to thank you for your time and looking forward to the roundtable.